So what's the number e? Okay, it's got a kind of weird abstract definition. If you take the expression 1 plus 1 over n to the n and let n get really, really big, okay, so you compute 1 plus 1 over 10 and raise it to the 10th. Then you compute 1 plus 1 over 100 and raise it to the 100th. So there's two sort of opposite forces that are going on here. When you take a number bigger than 1 and raise it to a big power, you expect that to be very large. But if I take a number that's essentially 1 and raise it to a power, that shouldn't be that big. So on the one hand, the 1 over n is getting very, very small. So as n goes to infinity, I'm up at the top of the screen, as n goes to infinity, 1 over n is very small. So 1 plus 1 over n is very, very, very close to 1. So I'm taking something very close to 1, and then I'm raising it to a very large number. The fact that the inside is close to 1 makes me think this isn't too big. The fact that the exponent is very big makes me think it's very big. There's two opposing forces going on here. It's not immediately clear how this resolves itself. As you let n get bigger and bigger and bigger, it actually settles down on one particular value, and that number is what we call e, and it's approximately 2.71. So, I encourage you, play around. Compute 1 plus 1 over something to that power. 1 plus 1 over 10 to 10, 1 plus 1 over 100 to 100, 1 plus 1 over a million to the millionth power, and see what happens. You're very quickly going to get 2.71, etc., and it's not going to change very much. Okay, so here are a couple of values for small. Here are a couple e to the x's. So remember, e is approximately 2.71. So we can use it as the base of an exponential function. Now you might be thinking, why on earth would I want to do that? 2 to the x, 3 to the x, 10 to the x, those numbers I can compute. E is this crazy thing. Why would I want to use it? For calculus reasons. When it comes to doing calculus and advanced computation with these exponentials, you want to be using this as your base, trust me. Okay. So e is approximately 2.72. Okay, I tend to round it off to 2.71. I think the next decimal point is a 6, so it should be properly rounded to 2.72. And then when you square it or take 1 over it, you get these other values. So we have, it's definitely bigger than 1. So I get an exponential curve that goes up to the right. And there it is. So can you graph the following? Note that this plus 2 is in the exponent. So begin with e to the x. Let's take care of that exponent. Fine, let's take care of the negative sign. So now I have negative e to the x. I reflected it across the x-axis. Now let's take care of the exponent. That is a left shift by 2 units, which radically changed the intercept, I want to point out. So instead of taking this intercept and trying to shift it left, well, now it's not an intercept. Since I shifted left by 2 units, I want to ask what height was corresponding to x equals 2. Now that height is corresponding to x equals 0. That's now your intercept. Negative e squared, about negative 7.39. But anyway, there's the graph. The domain is still all real numbers, nothing changed there. The range, since I didn't shift up or down, the range was just determined by this reflection. It's all negative numbers. The horizontal asymptote doesn't change either. Okay. So play around more with exponential functions. There's many examples in the book and practice problems. The next property of exponents that's handy to know, since exponential functions are one-to-one, because they're either increasing or decreasing according to whether a was bigger than 1 or less than 1. Remember, we don't let a equal 1, and we certainly don't let a be negative. So exponential functions are one-to-one. Actually, while I have some nice empty space, I'll just add. Remember, if a was bigger than 1, the graph looks like this. It's increasing, it's one-to-one. When a was less than 1, it was a decreasing, but still one-to-one. What would happen if a equals 1? I would just get the curve y equals 1 to the x, which would just be the horizontal line y equals 1, which is not one-to-one. Okay, what if a was negative? Now we've actually got some really bad problems. For example, let's just let a equal -1. Well, a to the x would be -1 to the x. If x equals 1, I'd get out -1. If x equals 2, I'd get out +1. If x equals 3, I'd get out -1. But that's not even the whole story. What if x equals 1/2? Then I would have the square root of -1 wouldn't exist. The domain would be terrible. Okay, strictly speaking, it's all rational numbers whose denominator in reduced form is not even. But like, this is just a terrible way to put it. You also don't want the 0 in there for technical reasons. Like, negative bases are just a nightmare. So we just throw these out altogether. No negative bases. If the base is 1, it's just boring. So really, either the base is going to be less than 1 or bigger than 1, but it's always going to be positive. Okay. But since these are one-to-one functions in these two scenarios, these are one-to-one, therefore, if I had the same output, I must have had the same input. Because remember, one-to-one means two different inputs must give two different outputs. So if the outputs were the same, then the inputs were the same. So we can use that to solve exponential equations. So let's work through this first one. Copy down the second one, because I'll ask you to do that on your own, but we'll work through the first one together. Okay, so 9 to the 2x minus 5 equals 27 to the x. Hopefully you wrote down. Now let's work through this first one. 2 to the x plus 2 equals 8. I don't have the same base on both sides unless I change 8 to be 2 cubed. Because now I have 2 to the x plus 2 equals 2 cubed. But hey, exponential functions are one-to-one. Therefore, the exponents must have been equal. X plus 2 must equal 3, and therefore x is 1. So can you do a similar trick with part B? Can I represent the left and right of B to have the same base? You can. You want to go with 3. Because 9 is 3 squared and 27 is 3 cubed. So now I can have a 3 as the base on both sides, but we're going to need to use properties of exponents. The left is 3 squared to the 2x minus 5, which changes to 3 to the 2 times 2x minus 5. Similarly, the right was 3 cubed to the x. That's 3 to the 3 times x, which means the exponents are the same because now the base is the same. Now I can distribute and solve for x. So there's your solution, x equals 10. Okay, in the next video, we'll come back and we'll do similar things, but with a base of e.